All right. Good morning, everybody. So, like I said last time, um, we really need to establish this bijection um, between the zero grade of the localization at f and g, and then of course the spectrum of that to the distinguished opens on these g over f fractions. Because that's what ties together the whole like project construction and gives us the ability to like reference back projective curves as like affine opens. So um, basically, um, I'm gonna walk through a solution that I feel okay with, and I don't know if this is entirely right, but I am also a third year undergraduate, and so if you're watching this, hopefully you take everything that I say with quite a few grains of salt. And if you figure out that I've done something wrong, please comment because I would love the feedback. So yeah, if it's not obvious, I'm not super confident about this one. Okay, so if we let t be the quotient that's going on here. Um, Then we want to have this map as constructed as like the first side of the map, and then we want to construct a second side of the map that is an inverse to that. And so the first map is a little easier. So if we just pick an arbitrary u um, in, in this thing, then it's going to look like this. And as long as our degree is, n times the degree of f for some n, um, this cancels out to be degree a, right? So basically the idea here is that s over f to the n has degree, n over a minus n, since the degree of s is na. And so then this guarantees that we're kind of staying in the domain that we want. Well, then u over our localizing factor of t to the k should be getting set by this map we're constructing to a distinguished open over here, or to something that maps to a distinguished open. And so basically the idea is that this should be a distinguished open. So, okay. Well, let me walk through the intuition here. So we want to send this to itself, and then we want to add this f to the b, g to the a, times this factor of localization. What we really want, though, is we want this to go over to a distinguished open. And then it's not in there, but like the inside is in there. And I think that gives us the one side. And yeah, the idea is that this piece lands in the same degree as like what we want. Um, okay, so then our inverse map. Um, Here's where I think maybe something has gone wrong because this is not going from hold on. Yeah, these both need to get mapped to distinguished opens or to ideals. This should be coming from a distinguished open. Because this first direction is this direction. So that's a problem. I mean, then I guess the thing, so if we remove this and we remove this and this and this, the thing that is happening here is that these functions do correspond to each other. I think it's just that they're distinguished sets, or their identity within spec needs to be identified, right? So instead of being in just the zero grade, we want this ideal in spec. But then similarly, we don't want just this polynomial. We want what it corresponds to in spec. I think that fixes it. And then similarly here, we want to be sending things instead of on the inverse map that is currently written out. We want to send things basically from spec to spec. And the key note here is that in our setup, this is a subset. And so this is definitely it's not going to take all. Well, no, it is going to take all of the domain. No, because it's only well defined on the G over Fs. So no, it's fine. Okay. Okay. So we're putting X into our domain, and we're saying it looks like S over F to the N, G to the M, as long as it's in degree NA plus MB, with the idea being that we are able to kind of cut off this M and this M, and we're left with A plus B. And then that gives us degree 1. Okay, pick K greater than or equal to the floor function of M, or the ceiling function of M over A. If it's not obvious, I did get part of this off of Math Stack Exchange. This is one of those moments. I'm not exactly sure where this came in. And clearly there have been some things that were misunderstood. So, you know, always work through a solution, right? So X is equal to this thing, but we can multiply in on the bottom f to the bk, or 1 over f to the bk, and then 1 over g to the ak. And then this g to the m moves up to the minus m. And we're not multiplying in, we're multiplying in 1, right? So we have 1 there, we have 1 here. So this is just moving things around, multiplying by 1. And then we can look at this as t to the minus k because we define t to be this thing. And it's t to the minus k because it's flipped. So this is t to the minus 1. And then we want to take this portion, which is in our 0 grade, and since the degree of the numerator is what we want it to be, the degree of the denominator basically makes this degree 0. We want our inverse map to send, and now this is where we have to change some things, but we want it to send this ideal class spec over to this point in other spec. And so we have this kind of inverse mapping where we can take one and represent it as the other and push them back and forth. Now, this does not prove that it's surjective or injective. Now, I think having a left and right inverse. I think having a right inverse implies surjectivity. A left inverse implies injectivity if and only if you accept the axiom of choice. So I think that we can maybe skirt by on that. But then also to get an isomorphism of spec, we really need this. So we have it as a set, but we need it as a topological space and a structure sheaf. And I'm suddenly realizing that is not something that has been written out here. I mean, clearly distinguished opens map to distinguished opens. Like, it is a homeomorphism. That is clear. Right? So we'll say psi is really the forward direction. Inverse, admit, homeomorphism on spec, but we still need an isomorphism of our structure sheaf, abbreviating heavily here, where X is spec SFG0, Y is spec and it's not that, it is D of F to the A, G to the B, G to the A, F to the B. Hold on. G to the A, F to the B. Okay. Huh. I mean, Wouldn't it be the underlying functions getting sent to the underlying functions? Because we're looking at basically the ring of regular functions. And
Yeah, I'd
these
assume
are
so.
like maybe that is the original. This is achieved by phi prime sending SF to the N, G to the M to and then phi prime inverse. Oh, inverse of um, u over t to the k getting sent okay. So mapping the underlying functions. Um, okay. And I think that that completes it. Okay. So that ties up a lot of loose ends. Um, so let's go ahead and take a look at chapter 5. Any questions, comments, concerns before we do that?
No.
Okay. All right. So some properties of schemes. Now that we've defined the notion of a scheme, we can define some useful properties of schemes. As you see each definition, you should try it out in examples of your choice, such as your favorite schemes of the form spec C over x1 through xn, mod sum ideal. Okay, that's a really helpful note. So 5.1, topological properties. So the definitions of connected, connected component, irreducible, irreducible component, quasi-compact, generalization, specialization, generic point, Noetherian topological space, and closed point were given in chapter 3. You should have pictures in your mind of each of these notions. Exercise 3.6 shows that affine n space is irreducible. This argument behaves well under gluing, yielding a first theorem that projective n space is irreducible. And so yeah, this just works out if affine n space is irreducible and we glue in an extra affine space with our projective way of gluing things, it stays irreducible. And I think that that is the core of what we're getting at here. Okay, exercise 3.7f showed that there is a bijection between irreducible closed subsets and points for affine schemes. The map sending a point P to the closed subset of P is a bijection. Show that this is true of schemes in general. So, theorem, P getting mapped to P closure is a bijection for all schemes, i.e. irreducible closed subsets, points of schemes. Yeah. I don't feel like that's something that needs a lot of proving. Right? Like, because we have, it's so easy to take projective coordinates on triple overlaps and then push back.
Yeah.
Okay. Prove that X is a scheme that has a finite cover. Or, oh, oops. Here. If X is a scheme with a finite cover, X is equal to the union I equals 1 to n spec AI, where AI is Noetherian. Then X is a Noetherian topological space. And this defines X as a Noetherian scheme. Hint showed that a topological space is a finite union of Noetherian subspaces is itself Noetherian. Yeah, so Noetherian topology is descending chain conditioning on subspaces. And so if we pick, I'm going to draw this visually and then formalize. If we have all of X, and we pick some chain of subsets, then we know, at the very least, that there is some cover of some finite cover of these chains of subsets. And these chains of subsets contained in these covers, say AI plus 1 for the visual example, are Noetherian. And so this must stabilize eventually. Basically, proof is let V contained in X, and we'll call it V bullet, and this will be an infinite sequence, B such that X contains V1, contains V2, contains V3. Want to show that there exists an N in Z with Vn equal Vn plus 1. Oh, let's make this a capital N. For all n greater than or equal to n. Okay. Well, V1 is contained in a union I equals 1 to j of AIs, which are Noetherian, and so the subspace I equals 1 to j of AI is a Noetherian topology. Thus, V stabilizes at the stabilization determined by the last the first containment. Where we have VI is contained in AK for some I and K. Basically, the first time we have a perfect subset, it's not like splitting over. It's going to be heavily contained in one of them. If that makes sense.
It does.
Okay. And so we get the desired result. Quick corollary of this is that projective K-space and projective space over Z are Noetherian topological spaces because we built them out of a finite number of spectra of Noetherian rings. Okay. Theorem. A scheme X is quasi-compact, or better known as just compact, if and only if it can be written as a finite union of affine opens. And then really what this is saying is that Pn over A is quasi-compact for all rings A. This was what gave us like the whole Louisville's theorem thing earlier, much earlier. But yeah, so literally this is basically the definition of like the backwards direction is the definition. And then the forwards definition is that, well, there exists a finite cover of X for every infinite open cover. And then these happen to be affine opens. And like in the case of projective and quasi-projective, it's by construction, and in the case of actual affine schemes, it is just the case. So yeah. Is that too loose of a proof technique?
Yeah,
It is?
I think so.
No, no. I asked if it's too loose of a proof technique.
Oh, I heard is that a good proof technique. I'm sorry.
Oh. I was like, damn, okay. All right, we can
No,
make this more
that's all right.
rigorous.
No, it's not. I mean, it's not terrible.
Okay. Yeah, I mean, this isn't like a super crazy claim.
Yeah.
Um, okay. Um, theorem quasi-compact schemes have closed points. Um, i.e. for every p in X, there exists a closed point in P closure. Um, not empty. Hmm. Okay, proof. Let UI I in cover X. Let P in X. Then really there exists a finite subcover j equals 1 to n covering X with P in UK for some K. Um, P closure. Um, I'm just stuck. I don't know what. This is not a good thing to be stuck on. Um, um, well, this looks like all of the things containing P, which is the vanishing of P. This feels like it's about to try and do something analysis adjacent.
Uh-oh.
I mean, and then take VP intersect UK, which is not empty. And then that's the proof. And that works. That does work. Okay. This exercise will often be used in the following way. If there is some property P of points of a scheme that is open, then there is some open neighborhood of that point such that all of the points in the open neighborhood have the property. Then to check if all points of a quasi-compact scheme have that property, it suffices to check only between the closed points. This provides a connection between schemes and the classical theory of varieties. The points of traditional varieties are the closed points of the corresponding schemes. In many good situations, the closed points are dense, but this is not true in some fundamental cases. Okay. Oops. Well, that makes sense, at least on how to use it. Um, so I'm gonna make a definition, and then we can stop there, and we'll come back at 10.
Okay.
So definition. So quasi-separated schemes. Quasi-separatedness is a weird notion that comes in handy for certain people. We will later realize that this is really a property of morphisms, not of schemes. Most people, however, can ignore this notion, as the schemes they will encounter in real life will all have this property. A topological space, quasi-separated, if the intersection of any two quasi-compact opens is quasi-compact. The motivation for the separatedness in the name is that this is a weakened version of separated, for which the intersection of any two affine open sets is affine. So yeah, the theorem about this that I will end this session with is that a scheme is quasi-separated if and only if the intersection of two affine opens is a finite union of affine opens. And this just directly follows from the definition of quasi-compact. Right, so quasi-separated implies the intersection of two affine opens, which are contained in quasi-compact opens, have an intersection, which is quasi-compact, which is a union of affine opens. So the forward direction is just right up definition. The backwards direction is just saying that there exists this containment and that builds the open cover and is finite.
Yeah.
So we will pick up with more quasi-separatedness in like 30 minutes. I'll go ahead and stop.